Welcome to my channel Phi Concepts CHM. This is the seventh part of Conduction in Semiconductors, where we will see about the continuity equation. Continuity equation. If the equilibrium concentration of carriers in a semiconductor is disturbed, the concentration of the carriers varies with distance and time. The continuity equation is a differential equation which governs this functional relationship. It is based on the fact that the charge can neither be created nor destroyed if generation, recombination, drift and diffusion are all taken into account. Consider an infinitesimal element of volume A, volume of area A and length dx. Average hole concentration inside this volume A dx can be denoted as P. The mean lifetime of holes can be denoted as tau P. So in tau P, if P holes recombine, then how many holes will recombine in 1 second? That will be P upon tau P. Number of holes per second will be lost by recombination per unit volume. E is the electronic charge. Because of recombination, the number of coulombs per second decreases within volume. That will be equal to E into A dx into P upon tau P. Equation 1. Let G be the thermal rate of generation of electron hole pairs per unit volume. The number of coulombs per second increases within the volume and is given as E into A dxg. Equation 2. In general, the current will vary with distance in semiconductor. The current entering the volume at x we will denote as I, and which is in the current leaving at x plus dx will denote as I plus di. So the number of coulombs per second decreases within the volume will be equal to di. Equation 3. So these are three effects happening. One is recombination, second is generation of electron hole pairs, and third is the current flowing through the semiconductor. So because of the above three effects, density changes with time. So the total number of coulombs per second increases within the volume, which can be given as E into A dx into dP by dt. Equation 4. Since charge must be conserved, this equation 4 should be equal to the sum of these three equations. So EA dx dP by dt is equal to minus EA dx P by tau P, minus because there is a decrease, plus EA dx into G minus di. Here minus because there is a decrease. Equation 5. In thermal equilibrium, if the field is not applied, the hole density attains a constant value P0. So I is equal to 0 and dP by dt is also 0 as the concentration or the density is remaining constant. From equation 5, this is equation 5, dP by dt is 0, so this is 0, and this P becomes P0 because it is constant, and di the current is 0. Rearrange the equation. Ea dx into G is equal to Ea dx into P0 by tau P. Ea dx will get cancelled out and we get G is equal to P0 by tau P. Equation 6. Rate at which holes are generated thermally is equal to the rate at which holes are lost due to recombination under equilibrium conditions. This we get from equation 6. Also, the current I, which we had seen in the previous video, is the sum of the diffusion current and the drift current. So that is the equation. We can differentiate this equation, so that will be di by dx is equal to minus ae dp into, differentiate this, that will be d square p by dx square plus ae mu p into d by dx of p epsilon. Equation 7. Epsilon is the electric field. Substituting equation 6 and 7 in equation 5, we get Ea dx dp by dt is equal to minus Ea dx p by tau p plus Ea dx p0 by tau p plus Ae dp into d square p by dx square dx minus Ae mu p d by dx of p epsilon dx. Divide the equation throughout by Ea dx, you get this equation. Ea dx will get cancelled out. Here the denominator tau p is the same, so it is taken as minus of p minus p0. Rest remains the same. Same equation we have written down as deba p suffix n. We have put these subscripts. Deba p n upon deba t is equal to minus pn minus pn0 upon tau p plus deba p into deba square pn upon deba x square minus mu p deba by dx deba x of pn epsilon. Equation 8. This is the equation of continuity, which is the equation of conservation of charge. The subscript n is added to p and p0 as we are considering the holes in the n-type semiconductor. Also, p is a function of t and x, time and distance. Therefore, partial derivatives are used. Now we will see the three cases of continuity equation. Case 1, we will consider concentration is independent of x and with zero electric field. So consider a situation with E is equal to 0 and concentration is independent of x. Example, the radiation falls on the semiconductor and raises the concentration to Pn0 bar, which is greater than Pn0. Equation 8, that is a continuity equation, will then become E is 0 and here the concentration is independent of x, so both these terms will go. So what do you get is dPn by dt is equal to minus of Pn minus Pn0 by tau p. Equation 9. Solution of this equation can be written as Pn minus Pn0 is equal to Pn0 bar minus Pn0 into e raised to minus t by tau p. Equation 10. Time constant with which concentration returns to its normal value. It's the time taken, that is tau p, is the time taken for the injected concentration to fall to 1 by E of its initial value. Now case 2, where we will consider the concentration is independent of T and with zero electric field. So E is 0. Steady state has been reached. So delta Pn by delta T is equal to 0. It is the concentration is independent of time. So equation 8 will become delta Pn by delta T is 0. Epsilon is 0. So only these two terms will remain. Rearrange this equation in this way. You can take dP on the other side. We get delta square Pn upon delta x square is equal to Pn minus Pn0 upon dP tau P. dP tau P can be written as Lp square. Equation 11. Solution of this equation will be Pn minus Pn0 is equal to K1 into e raised to minus x by Lp plus K2 into e raised to x upon Lp. Equation 12. Where K1 and K2 are constants of integration. And Lp is equal to square root of dP tau P. Equation 13. This solution can be verified by substituting equation 12 in equation 11. Now consider a very long piece of n-type semiconductor extending in positive direction from x is equal to 0. Since the concentration cannot become infinite as x tends to infinity, so we will consider K2 is equal to 0. Therefore, Pn minus Pn0 will denote as Pn of x. This is the injected concentration which is greater than the equilibrium value Pn0, which is a function of x. Assume at x is equal to 0, we can write this equation as Pn of 0 is equal to Pn of 0 minus Pn0. This is at x is equal to 0. To satisfy this boundary conditions, what we can do is we can put x is equal to 0 and K2 is equal to 0 in this equation 12. We will get K1 is equal to Pn of 0. Therefore, we can write down Pn of x is equal to Pn minus Pn0 is equal to Pn of 0 into e raised to minus x by Lp. So we are substituting everything in this equation 12. We get equation 14. Lp is the diffusion length for the holes. It is the distance into the semiconductor at which the injected concentration falls to 1 by E of its value at x is equal to 0. It can also be interpreted as the average distance which an injected hole travels before recombining with an electron. We can verify this statement. This is a semiconductor. This is at x is equal to 0. This is one end of the semiconductor. We are considering the distance x is equal to 0. This distance into the semiconductor will take as x. And this distance is dx. At x is equal to 0, the concentration we denote as Pn of 0. And at x we will denote as Pn of x. So from the figure and equation 14, we can write down, we can differentiate it as dPn upon dx is equal to Pn of 0 into e raised to minus x by Lp upon minus Lp. Taking the mod of this equation, this minus sign will go. So mod of dPn, we are taking dx on this side. So mod of dPn is equal to Pn of 0 upon Lp into e raised to minus x upon Lp into dx. Equation 15. Where dPn is the number of injected holes which recombine in the distance between x and x plus dx. Since each hole has travelled a distance x, The total distance traveled by mod dpn holes can be given as x into the number of holes, that is mod dpn. Therefore, the total distance traveled by all the holes, what you can do is we will integrate this product with the limits from 0 to infinity. Therefore, the average distance will be x bar is equal to this integral divided by the number of holes, that will be Pn of 0. So substituting this mod dpn here, Pn of 0 will get cancelled out. So equation 15 is substituted here. We get inside the integral as x e raised to minus x by lp dx. So we can integrate here, we can use the UV product rule. By keeping x constant, first we integrate the exponential, that will be e raised to minus x by lp divided by minus 1 upon lp with limits from 0 to infinity, minus, here there is double integral, so first we will integrate once, that will be minus x minus integral of e raised to minus x upon lp upon minus 1 upon lp, and differentiate x, that will be dx. Then this lp is taken on in the numerator, minus of lp into x e raised to minus x upon lp with limits 0 to infinity, plus again integrating this, we get lp into e raised to minus x upon lp upon minus 1 by lp. Then we can substitute the limits in this step, and finally we get lp square. So x bar will be equal to 1 by lp into lp square, that is equal to lp. So x bar is equal to lp. We have verified the statement, equation 16, which is the mean distance of travel of the hole before recombination. Then the third case is concentration varies sinusoidally with T and with 0 electric field. E is 0, but the injected concentration is varying with angular frequency omega. Then we will have to write down in phasor notation, Pn of xt will be written here. One part is the x depends upon x, the other part depends upon time. So Pn of x into e raised to j omega t. Equation 17. Substituting this in equation 8, this is equation 8, the continuity equation. This is delta Pn upon delta t, so we differentiate this equation. So Pn of x will be a constant as it doesn't depend upon t, it just depends upon x. So Pn of x we can directly write, and we have to just differentiate e raised to j omega t, so that will be e raised to j omega t into j omega. Then Pn minus Pn0 by tau p, here it is written as minus of Pn of x e raised to j omega t upon tau p plus dp into delta square. Pn we will again substitute in this form, Pn of x e raised to j omega t, and epsilon is 0, so the third term will not be there. Dividing throughout by e raised to j omega t, you get this equation. Rearrange the equation in this form, that will be dp d square Pn of x upon dx square is equal to j omega Pn of x plus Pn of x upon tau p, taking dp on the other side in the denominator. So you get d square Pn of x upon dx square. Multiplying this first term, multiplying and dividing by tau p, you get tau p in the denominator. So dp tau p will be there in the denominators of both these terms. So taking here Pn of x common, we can write down here d square Pn of x upon dx square is equal to 1 plus j omega tau p upon dp tau p into Pn of x. Equation 18. dp tau p then can be written as Lp square. Equation 19. Since Lp is equal to square root of dp tau p. Now at zero frequency, omega is 0, that is the concentration is independent of time, and then the equation of continuity, that is the equation number 19, which we have got just now, will become this term in depending on time will go. So what remains is Pn of x upon Lp square. Is equation 20, which is similar to what we had got in case 2, where we had considered the condition that the concentration is independent of time. So the continuity equation is completely discussed. Thank you for watching this video.